So let's start. It's time. So a few months ago, I had to build a GraphQL API consumed by a Blazor WebAssembly application. I never had to work with GraphQL before. Quickly, I've realized that GraphQL could have saved me some time on past projects. And after this project, I've taken a step back and watched all the backend API technology options we have in the .NET space, because I realized that I was maybe a bit too focused on our default go-to REST-like API, so-called ASP.NET Web API. We all go to this default framework in general most of the time, but we have other options. So REST, but also gRPC API. We have GraphQL API, and we also have SignalR API. Their implementations are built most of the time on HTTP 1 or 2, and when they have some bidirectional communication feature, they rely on WebSocket or server sent event, and two of them are deeply linked to a protocol or a transport protocol. gRPC is deeply linked to HTTP2, and SignalR is deeply linked to HTTP 1 and server-side event or WebSocket. It's not so true for REST and GraphQL API, but we'll discuss this in the rest of the presentation. So my assumption after taking this step back is that it's not so easy for new developers, newcomers to the .NET space, or even for people who are like me, who are focusing on REST-like API and who have used ASP.NET Web API a lot in the past, to evaluate the pros and cons of using one technology over the other. So during this presentation, I'll go over the concept of those four backend API technology, and I won't demonstrate how to bootstrap them. So I don't want to disappoint you, but in the description of the talk, I said that I will quickly show how to bootstrap them, but when I was preparing this talk, I realized it's an overview talk, and just spending 2 minutes to demonstrate a quick start of GraphQL API or SignalR API wouldn't have any value. It's more a conversation about those four technologies. And I've seen that there are more deep talk on SignalR today. Even there is a workshop on GraphQL API running. So if you want deep dive on one of those technologies, you can today. And the idea is more to have an overview of those technology and to know how to pick one over the other depending on your use case and what you need to achieve in your project. So this is really an overview session. Don't expect deep technical details, but rather a discussion. So before going further, let me introduce myself. I'm François Bouteruche. I'm a senior developer advocate at AWS. My day-to-day job is being the developer zero for all things related to .NET at AWS. So testing new feature, new service with the .NET developer, C# developer perspective, and giving feedback to our service teams saying, hey, this is really good, this is not good, you should improve this. So that's one part of my job, and the other part is being the link between AWS and the .NET community by living and breathing like a .NET developers, being in .NET Meetup, being at .NET Conference, running .NET interviews. I try to have a lot of discussion with .NET developers to get their feedback on .NET in general and on .NET on AWS when you're using AWS to pick those feedback and get them to the service team so that they improve our services. So if you have any feedback you want to share with me, you can reach out to me on LinkedIn, on Twitter, on Mastodon, or you can even come and chat with me after the session. I will be happy to discuss with you. So let's move on. Does REST really rule the .NET Backend API world? My short answer is no, and it doesn't matter. And no, I will explain why. Let's go back to the root of what is REST. And the root is in Roy Thomas Fielding's PhD dissertation, which he has published in 2000. So here is a link, and don't be afraid, it is human readable. Yes, it is a PhD dissertation, but it's human readable. I've read his dissertation, and I was really surprised how easy it was to read this. And I think it's one point in favor of his awesome work. He summarized all the things he worked on very clearly. So even if you're not a computer scientist, you can read his thesis and understand what he is talking about. And this is the source of truth about REST, because Roy Thomas Fielding is the one who have defined REST. And after reading his dissertation, I've read a lot of content on the internet about REST, and often they are wrong. People say, hey, REST is this or this, and it's totally wrong. So I would recommend sometime, if you want to deep dive on REST, to read his dissertation. It's really worth a read. So what is REST? It's an architectural style. It's not a framework, it's not a library, it's not a technology, it's an architectural style. It means representational state transfer. So the idea is that you transfer the representation of the state of a resource. REST is really resource-oriented. And what you transfer between a client and a server is the actual or the desired resource state. That's roughly the idea. And Roy has defined REST with 7 constraints. The first one, a REST architecture must follow the client-server constraint. Easy. You have a client, it sends a request to a server, the server answers and responds to the request. Pretty easy. The second constraint is stateless interaction. So the request sent by the client must contain all the information required by the server to process the request. The server must not store any context about its interaction with the client. The third constraint, is cache. So when the server answers to the request, it should make it clear if its answer can be cached or not. So it's a nice thing about the work of Roy Fielding. More than 20 years ago, he was already thinking about issue we are facing today about the scale of internet, the scale of our website with millions of users, and if we don't want to go down our database, we have to cache our requests. So he was already thinking about all this issue more than 20 years ago. The fourth constraint is uniform interface. So the idea is to have an option to make your architecture independent of the system and the language you are using. The sixth constraint is layered system. Your client sends a request to a server. If your service needs to send another request to other backend servers to process the request, the client must not know this implementation details. He only sees one server. So that's a layered system. And the last constraint, and I think this one may have been influenced by Java applet at that time, is code on demand. Basically, it means that the client can download code from the server to execute locally this code. This is the only optional constraint. All the other constraints are mandatory, so that you can say, my architecture is a REST architecture. So let's take a closer look at the uniform interface, because in fact there are 4 sub-constraints for this one. So unique identification of resources. Any resource that you API manage should be uniquely identified. You manipulate your resource through their representation, not through procedure or method. You manipulate your resource through their representation. The message that goes from the client to the server, or from the server to the client, should be self-descriptive. And last constraint, you should follow the hypermedia as an engine of application state constraints called @OS. This one means that when the server sends back the resource description, so the client requests a resource, the server sends back the resource defined by its representation. It should also send links to additional URLs if you want to get details about this resource. Let's say you have a blog post API. Your client sends a request to request the detail of a blog post. So you get the title, you get the description, and you get some links to follow up, for example, to get the detailed information about the author of the post. You have a link to make an additional request to get, for example, the comments that have been added to the blog post. So those links are in the server response. You don't have to guess how to get those additional information. The links are in the response. So what is a REST API? It's basically any API that implements REST constraints, whatever the protocol and component implementation. So REST has nothing to do with HTTP. In fact, HTTP 1.0 and 1.1 development has been used to validate REST architecture style by Wolfielding during his thesis. He was part of the working group who defined HTTP 1.0 and 1.1, and HTTP 1.1 protocol is built to be the ideal protocol to follow REST principle and constraints. So REST is not HTTP, HTTP is not REST, but HTTP 1.1 has been designed to be the ideal protocol for REST. So what does it mean in practice for our backend API? Most REST API that you know don't implement @OS constraints. So they are not REST API. That's it. And that's okay. Implementing @OS can be worse, but it is not trivial. For example, in the early day of Netflix, they had an API, a public API, where they were implementing @OS, and they've stopped. Actually, you don't have any public API for Netflix for now, but in the early days, they have one API implementing this. So you can find some REST API implementing the @OS constraint, but it's not very frequent. And in the .NET space, we don't have any helper for this. In the Java space, you have Spring @OS framework that helps you to add links to your REST response, but you don't have any helper in the .NET space. So as there were a lot of confusion about all this, Leonard Richardson at QCon in 2008 proposed a REST API maturity model. So level 0, it's you are using one URI and one HTTP method. So basically, you don't follow at all. You don't follow the REST constraint because you have only one unique resource identifier to get all the resources your API has to offer. So, and only one HTTP method. Level 1 is you have one unique resource identifier for every resource, but you are still using only one HTTP method, for example, get or post. Level 2, you're pretty good. You are using one unique resource identifier per resource, and you are using HTTP verbs for what they mean. For example, if you want to get the resource, you will use the get HTTP verb. If you want to create a resource, you will use the post HTTP verb, and delete verb, put verb. So there is a lot of debate about, hey, we should use put and not post, or we should use post and not put. Okay, that's sterile debate. It doesn't help, and it's not part of REST. And level 3, you are implementing at OS, and you are implementing a true REST API. So ASP.NET Core Web API helps you to build level 2 in this maturity model. So that's what we get from ASP.NET Core Web API, and that's totally fine. That's totally fine. Personally, I've never implemented at OS API. So some challenges with REST-like API. Let's call them now REST-like API. Performance in microservice architecture. Data flexibility. So data flexibility, it means you are requesting a resource. If your resource have a lot of properties, and if you have many consumers, for example, they may be not interested by the same properties. But every time you send all the data you have on the resource, hey, here is my data about the resource, and now do whatever you want with those data. Even if some of the properties are not relevant for the consumer, you send the properties. Two-way communications. I told you, the client can request the server, but if the server wants to notify the client that there is an update on the data, no solution. And nowadays, we can have some needs about streaming requests and response. For example, I want to open a connection and stream some message to the server, or the server wants to stream some information to the client. Especially useful in some IoT scenarios, for example, where you have a device and you want to stream some data to the server. So that's some challenge with REST-like API. So let's start with microservices, because this is where the performance issue of REST-like API is the most important one. So if we are speaking about microservice architecture, we should recall that microservices should own their domain data. That's one of the best practice of microservice architecture. So does it make sense to transfer resource state between two services? Not really, because the service that gets the data doesn't own those data. Maybe he needs one of them, but it doesn't own the data, so it shouldn't store those data. So in microservices architecture, what we call remote procedure call is a valid approach. For example, I have backend API managing the speed of my car. I have another service who allow me to drive my car. If I want to increase the speed, I don't want to send, okay, no, this is your state, this is your speed. I just want to call my service and say, hey, increase the speed or decrease the speed. And that's it. So that's basically the idea. And for implementing remote procedure call, nowadays, a good framework, a good technology is gRPC. And let's talk about gRPC design principles. So, most important one is the first one: services, not objects; messages, not references. So, the idea of gRPC is to promote the microservice design philosophy and to avoid the pitfall of distributed objects. We just send message between services. The second one is coverage and simplicity. It means that the stack should be available on every popular development platform and very easy to use. I won't go into all the design principle of used to design gRPC because there are a lot, 16. You can find them at the URL here. At the beginning, gRPC was a Google technology, Google project, and now it's a Cloud Native Computing Foundation project. You can use it, and it's embedded in .NET. So gRPC in a nutshell, you have a C++ service, for example, which implement the gRPC server, and you have some clients, maybe in Ruby, maybe in Android and Java, maybe in .NET, and the gRPC stub and the gRPC server exchange proto request and proto response. So let's see the anatomy of protocol buffer message. So it's pretty easy. It's protocol buffer is a serialization protocol from Google. The nice things with protocol buffer is that they've developed the support of this serialization protocol the same way in each language they support. So you're sure if you are serializing this message in Java and you send it to a C# implementation, for example, you are sure it will interoperate. So this is for just defining a message, and then we can define a service. So here we have the greeter service, and we define a remote procedure, say hello, that receives a hello request and returns a hello reply. And we have both those messages defined here. So that's pretty simple. So the benefits of using gRPC is based on those definitions. It will automatically generate the client and the server code in 11 languages. So you are not forced to generate the code in 11 languages, but you can pick one of the 11 languages supported by gRPC. So .NET support gRPC. It's part of the .NET Core framework, ASP.NET Core framework, so it's fully supported. You don't have to install anything specific. It leverages HTTP2 performance improvement and more specifically the binary frame from HTTP2 to improve performance, and also the fact that with HTTP2 all your requests are not sequential, but you can send multiple requests from your client to the server and process those requests in parallel and not in sequence. It supports bidirectional streaming. So gRPC supports streaming. And you can stream from the client to the server, from the server to the client, or in both directions at the same time. And finally, there is an extension APIs to plug authentication, tracing, load balancing, and health checking. So for example, it's very fun, but you can, if you are in a trusted environment, like, let's say, some microservices in a Kubernetes cluster working together, you can implement load balancing on the client side. So rather than having your client sending a request that goes through a load balancer, and the load balancer to split the load evenly across your gRPC server, it's your gRPC client that does the load balancing work, because you are in a safe environment. Why you can do this with gRPC? Just for performance purpose. By doing this, you remove one hop, you remove some latencies in your network, even if they are in the same Kubernetes cluster. If you go through the load balancer, you introduce some latency. So for performance purpose, you can do this in safe environment. So let's move to the next question. What can I do if I have one API, multiple consumer, and multiple representations to serve? So this is a one-size-fits-all issue. REST-like resources have predefined representations. So if you want to optimize your API for reducing the number of requests, you highly end up with heavy message to serve all your clients with irrelevant data for most your clients. And it has some impact on your bandwidth, because you are sending a lot of data on your network that doesn't serve your clients. On the other side, if you are optimizing for transferring only the data your clients need, you will end up with small messages with little info and multiple requests to get all the required data. So that's the trade-off you have to do if you stick with a REST-like API. And if you don't want to stick with REST-like API, if you are open to other technologies, GraphQL comes to the rescue. GraphQL is a query language plus a server-side runtime for executing those queries. It's database or storage agnostic. On the server side, with the server-side runtime, you implement how to query the data. The specification of GraphQL is agnostic from transport protocol, but in practice, most implementation of GraphQL rely on HTTP and JSON objects. So, for example, we define here query, saying this is the query me, and it will return an object, a user object. And here I'm defining the user object, so the user object has an ID and a name. And then I'm defining some functions running on my server-side runtime. So one function here, query me, that take my request in parameter and return my user. And the second function taking my user object and returning just the name. So I provide this to my server-side runtime, and it will allow me to have an API that if I send this JSON object to my API, so here the important part is I'm saying, okay, I want to make a me query, and in the response, I just want to get the name. I don't care about the ID, so I just want to get the name. And this is what the server will return in response. Okay, here is the me object, and here is the name, Luke Skywalker. So here we have a small object, but imagine this with a graph, okay? Because it is called GraphQL on purpose. The recommendation, the best practice with GraphQL is to model your data as a graph, and to think about your data as the graph with relation, so that at the end you can in the best case, you can your consumer can do one request that query all the data it needs with only the property it needs. So, using GraphQL, the benefits: you query only the data your client needs. You can proxy multiple legacy data systems in one API. So we can say that we could do this too with REST API. But the nice things here is that you can query on the server side, you can query your legacy system and just choose which data you want to transfer to your clients. And depending on your consumer, the data you want to transfer is not the same. So if you are doing this with a REST API, you will likely end up with sending all the data you know about your user in every legacy system you have. So maybe you don't want to do this. The caveats with GraphQL is the learning curve, because it's a language, so you have to learn the query language. It's a new language. So it's not so easy at the beginning, but once you've learned the query language, it's pretty cool. Another issue is caching. Of course, as every request may be different, it's much more harder to cache your answer. There are some techniques to work around this, but yes, compared to REST, it's an issue. So what about real-time data updates? I need to go a bit quicker. What is the need? So standard HTTP flow, your client sends a request and your server responds. Okay, but what to do? What can I do if a data update occurs and I want to send a notification to all my clients to say, hey, for example, on my blog post, the number of likes on my blog post has increased, and I want to notify all the client apps who are currently watching my blog post. So we have a quick solution in the .NET space with SignalR. It's an open source library, part of ASP.NET. It implements server to client remote procedure call. So basically, your server call a procedure on the client side. It automatically chooses between WebSockets, server send events, and long polling. So the initial value proposition of SignalR was from a time where WebSocket support, for example, in browser was uneven. Same for server sent events. So the idea was, okay, the framework will detect the capabilities of the browser and decide if it starts with WebSocket, if it starts with server sent events, or if it starts with long polling. Long polling is basically just keeping the connection and having the client, the connection open and having the client keep requesting about data update. The caveats with SignalR is that it's strongly tied to .NET ecosystem. On the client side, you have implementation for JavaScript, .NET, and Java. On the server side, you only have .NET. So if you are implementing, let's say, a small application with a backend for front-end API, so the API you are implementing is only for the front-end you are building, that's fine. But here, if you are, let's say, implementing a public API, it's an issue because you will force your consumer to use SignalR on the client side. So you will force them to use the SignalR JavaScript library, for example, in their website, and they probably don't want to do this. So much more wide technology is GraphQL subscription. So it was not in the initial GraphQL specification, they've added this operation in the specification. So at the beginning, there were only two operations in GraphQL: query and mutation. So mutation is for sending a data mutation to the server. So here we have a mutation saying, okay, story-like mutation. So I have a message here, and I don't want to go into the detail, but it sends a mutation to the server. And they've added the subscription operation. So here I can send a subscription request to be notified of any data change. So how does it work? So let's say my client B and client C send a request a subscription to be updated of any data modification. Then my client A send a request for a mutation using the second operation I've defined. Then my GraphQL API will send an update to both client B and client C to let them know that the data has been updated. So most of the time, this is implemented with WebSocket, but you can find some implementation of GraphQL subscription using MQTT, for example. So here again, GraphQL subscription doesn't enforce any protocol, so you can find different implementation. So now we've seen all the technology, and here it comes a decision tree. So first, it's my opinionated simple decision tree for .NET developers. So it's my opinion. You can disagree. My colleague can disagree. I've tested it against my colleagues, so they are pretty fine with it. So, but you can disagree. That's fine. So the first question I would ask when starting a new project and thinking about which technology I should use is, okay, am I building an internal service-to-service API? If yes, the next question is, can I easily coordinate service update? Because something I didn't mention about gRPC is the fact that when you update the service definition, you can break the compatibility. So some service update needs to update the client too. So you have your client and your server is kind of strongly coupled. So you have to be able to coordinate service updates. If so, and in general, when we are working on a microservice architecture, we can choose gRPC API. If you answer no to both of these questions, the next question is, do I need or do you need two-way communication? If so, the next question is, okay, which kind of two-way communication? If it's client or bidirectional streaming capabilities, the next question go back to, can you easily coordinate service update? If yes, choose gRPC API. If you can't, reconsider. For example, those scenarios can be worse for IoT, where your IoT objects are online. You know your network is reliable, and you want to stream data from your IoT object to the server and from the server to your IoT objects. For those kind of use cases, gRPC can be a good candidate. If you don't need bidirectional streaming or client streaming capabilities, think about GraphQL subscription. I don't mention SignalR here on purpose because as I mentioned, SignalR is strongly coupled to the .NET space, and I didn't see any pure .NET shop for a long time now, so it's likely you have other teams in your company that are using Java or Go or JavaScript and Node.js, so you should be prepared to collaborate with them. So avoid technologies that couple your work with .NET. If you don't need two-way communication, okay, the next question is, do you need to support multiple clients with different needs? If so, GraphQL API is for you. And of course, in general, you don't have a GraphQL subscription alone. You have GraphQL subscription with a GraphQL API. And if you don't need, the next question is, okay, do you need to optimize for bandwidth? If so, go to GraphQL API, and if not, go to REST-like API. So, first part is for inter-service API, middle part is for real-time API, and the rest is for web API. And I have a disclaimer for you. This decision tree is for beginner and does not imply that any other alternative is not a good one. For example, some people have implemented inter-service API with GraphQL. Some people have implemented public-facing real-time API with gRPC, and that's fine. As long as you are fine with your choice, with the trade-off you've made, that's totally fine. The idea is really you have to know why you are choosing a technology. Other point I want to mention. Maybe you think REST-like API is alone as a right bottom, but it doesn't mean we don't need to use REST-like API anymore. In fact, I think it will continue to cover at least 80% of our needs, because all those questions, you won't say yes to one of these questions often. It's specific use case, it is specific needs, so often you will end with, okay, a REST-like API is totally fine for me, and that's okay. So this decision tree doesn't mean that we are letting REST-like API alone, that it's a dead end. No, not at all. It's just that before going to the default go-to solution of the .NET space, you should think about the other option. So that's it for today. Thank you for your attention. And if you have any question, I'm open to question.